Hello, this is Irene from Exam Help Lab. Today I'll be solving Physics Paper 2 ES Level Structured Questions 9702 Paper 2 reading 2 February March 2018. Question number 1, Part A, complete figure 1.1 to indicate whether each of the quantities is a vector or a scalar. So acceleration is a vector quantity, while speed and power are both scalar quantities. A ball is projected with a horizontal velocity of 1.1 meters per second from point A at the edge of a table, as shown in figure 1.2. The ball lands on horizontal ground at point B, which is a distance of 0.43 meters from the base of the table. Air resistance is negligible. Part 1, calculate the time taken for the ball to fall from A to B. So from A to B, it has a horizontal speed of 1.1 meters per second, which remains constant throughout, and it covers a horizontal distance of 0.43 meters. So the time interval from A to B for both horizontal and vertical parts of its motion is the same, and is distance divided by speed, which is 0.43 meters divided by 1.1 meters per second, and that is 0.39 seconds. So this time interval is the same for both the horizontal motion and the vertical motion. Part 2, use your answer in B part 1 to determine the height of the table. So now the vertical distance this ball covers from A to B, its initial velocity with which it starts its speed from the table is going to be 0. Air resistance is negligible, therefore its acceleration in the vertical motion is going to be of 9.81 meters per second square of magnitude. The time interval from A to B is going to be taken from the previous part, which is 0.39 seconds. So the vertical distance it covers is going to be ut plus 1 by 2 AD square. So S is equals to 1 by 2 into 9.81 into 0.39 square. And hence the distance or the height being covered from A to B is of 0.75 meters. Part 3, the ball leaves the table at time t is equals to 0. For the motion of the ball between A and B, sketch graphs to show the variation with time of the acceleration of the ball. So acceleration remains constant, which is 9.81 meters per second square for its vertical part, since it doesn't accelerate anywhere horizontally. So it's going to be a horizontal line on here. Now the vertical component of the displacement of the ball from A, so for the constant positive acceleration, which is 9.81 meters per second square, we are going to have an increasing graph on displacement versus time graph. Part C, a ball of greater mass is projected from the table with the same velocity as the ball in Part B. Air resistance is still negligible. State and explain the effect, if any, of the increased mass on the time taken for the ball to fall to the ground. Okay, so while air resistance is negligible, there will be no effect on time taken for the ball, even if its mass has been changed, because of the constant acceleration which acts on the ball, and that is 9.81 meters per second square due to gravity. So we are going to write that there is going to be no change in the time interval to reach point B from point A due to constant acceleration. And this kind of acceleration is also called acceleration due to free fall, and that is all due to gravity. Question number 2, part A, explain what is meant by work done. So this is force multiplied by distance in the direction of force. Kinetic energy, this is energy of an object due to its motion. Part B, a leisure park ride consists of a carriage that makes along a railed track. Part of the track lies in a vertical plane and follows an arc xy of a circle of radius 30 meters, as shown in figure 2.1. The mass of the carriage is 580 kilograms. At point X, the carriage has velocity 22 meters per second in a horizontal direction. The velocity of the carriage then decreases to 12 meters per second in a vertical direction at point Y. Now for the part where the carriage starts to move from point X towards point Y, show that the decrease in kinetic energy is 9.9 into 10 to the power of 4 joules. So this is going to be half into mass into change in speeds, which is of 22 square and then 12 square. So the decrease in the kinetic energy of the carriage is going to be of 9.9 into 10 to the power of 4 joules. Now calculate the gain in gravitational potential energy. So change in gravitational potential energy is going to be mass into G into H. Mass of the carriage is 580 into 9.81, and the height it rises to from A to B, which is the vertical distance it covers when it travels from point A until point B, that is of 13 meters, which is also the radius of the circular track. And the gain in gravitational potential energy is 7.4 into 10 to the power of 4 joules. Part 2 showed that the length of the track from X to Y is 20 meters. So the question is asking us to find the length of this track, XY. So this is something which math students would know, and that is that arc length is equals to this angle over here, which is 90 degrees, but it has to be taken in radians multiplied by the radius of the circle, which is 13 meters. So 90 degrees is equals to pi by 2 in radians multiplied by the radius of the circular track, which is 13 meters, and hence we have the arc length as 20.42, which is also equals to 20 meters. Part 3, use your answers in B part 1 and B part 2 to calculate the average resistive force acting on the carriage as it moves from X to Y. Okay, so changing kinetic energy and gravitational potential energy of the carriage must have resulted in resistive force. So the energy difference between both these decrease in kinetic energy and gain in gravitational potential energy is going to be energy lost due to heat or in a work done against air resistance. So the work done against air resistance is going to be the change in decrease in kinetic energy and the gain in potential energy, which is equals to 2.5 into 10 to the power of 4. Now work done against air resistance is equals to the resistive force into the distance it covers from X to Y, which is 20 meters, and hence we have the resistive force as 1250 newtons. Part 4, describe the change in the direction of the linear momentum of the carriage as it moves from X to Y. So when it starts to travel with horizontal velocity, it had horizontal momentum, and when it reaches position Y, it possessed vertical speed, so the momentum changes to vertical momentum. So we can write that it changes to horizontal, that it changes to vertical from horizontal. Part 5, determine the magnitude of the change in linear momentum when the carriage moves from X to Y. So here the carriage moves both horizontally and vertically. So first we must find momentum in both directions and then find the resultant momentum, which is the change they are asking us to calculate over here in this part. When it travels horizontally, it had a momentum of 580 into 22. When it travels vertically, it had a momentum of 580 into 12. And the resultant of them is what they're asking us in this part of the question, and that is equals to 580 into 22 the whole square plus 580 into 12 the whole square. And this is equals to 1.5 into 10 to the power of 4 newton second. This is the resultant change in momentum of the carriage. Question number 3, part A. For the deformation of a wire under tension, define stress. So stress is equals to force divided by area. Strain is equals to extension over original length of the wire. Part B, a wire is fixed at one end so that it hangs vertically. The wire is given by an extension by suspending a load F from its free end. The variation of F with X is shown in figure 3.1. The wire has cross-sectional area of 9.4 into 10 to the power of -8 meters square and original length 2.5 meters. Part 1, describe how measurements can be taken to determine accurately the cross-sectional area of the wire. So cross-sectional area of the wire is equals to pi r squared, where r is the radius of the wire. So what we can do is that we can measure the diameter, and that way we can measure radius 2 by dividing diameter by 2. We can measure diameter with the help of micrometer screw gauge or vernier calipers, either. You can write that with the help of micrometer. So we have to take several readings of the diameter of the wire. And that should be followed by taking the average of all those values. But to determine the Young modulus E of the material of the wire, Young modulus is equals to force into original length divided by area into extension. 1 Newton being exerted on the wire, it produces an extension of 0.2 millimeters. So 1 newtons of force and original length is of 2.5 meters divided by area is 9.4 into 10 to the power of negative 8, and 1 newton of force produces an extension of 0.2 millimeters, which is 2 into 10 to the power of negative 4 meters. And that's how we get a Young modulus of this wire as 1.33 into 10 to the power of 11 pascals. Part 3. Use figure 3.1 to calculate the increase in the energy stored in the wire when the load is increased from 2 newtons to 4 newtons. So increase in energy is going to be calculated by calculating area under the graph. So 2 newtons and 4 newtons. So when the force being exerted on the wire was 2 newtons, we had an energy of half into 2 into 0.4 divided by 1000, and when the force was increased to 4 newtons, we had an energy of half into 4 into 0.8 by 1000, and the change in both these is going to be 1.2 into 10 to the power of negative 3 joules. Part C, the wire in B is replaced by a new wire of the same material. The new wire has twice the length and twice the diameter of the old wire. The new wire also obeys Hooke's law. So this new wire also obeys Hooke's law. On figure 3.1, sketch the version with extension x of the load F for the new wire from x is equals to 0 to x is equals to 0.8 millimeters. So now the newer length is the 2.5 into 2, which is 5 meters, and the newer area is going to be the double of. Now the newer area is going to be, for that we first have to calculate the radius of the old wire, which is 9.4 into 10 to the power of negative 8 divided by pi. And this is the radius of the old wire. We should first multiply this radius by 2 and then find the newer area, which is going to be pi r square again, and hence we have the newer area as 3.76 into 10 to the power of negative 7 meters squared. Now the new wire is of the same material, so Young modulus of this is going to be constant, which is 1.3 into 10 to the power of 11 pascal. Now it's time to find out the force being exerted that causes 0.8 millimeters of extension on this double the length and double the area wire. So force is equals to Young modulus, which is 1.3 into 10 to the power of 11 into the area of the new wire, which is 3.76 into 10 to the power of negative 7, into the extension, which is 0.8 millimeters, so 0.8 divided by 1000, and this whole should be divided by the newer length of the wire, which is 5 meters, and hence the force which causes an extension of 0.8 millimeters, this is of 8 newtons. So the force that causes 0.8 millimeters of extension is 8 newtons, and we'll have a straight line again from 0, 0 to 0.8 on 8, since it obeys Hooke's law. So we're going to have a straight line. Question number 4, part A, state the conditions required for the formation of a stationary wave. So the two waves, which are the incoming waves that are of the same frequency or wavelength, and are in opposite directions, they are traveling in opposite directions to each other. When they overlap, that forms a stationary wave. Now part B, the sound from a loudspeaker is detected by a microphone that is connected to a CRO. Figure 4.1 shows the trace on the screen of the CRO. In air, the sound wave has a speed of 330 meters per second and a wavelength of 0.18 meters. Calculate the frequency of the sound wave. So frequency is equals to speed of the sound wave divided by the wavelength. Speed of the sound wave is 330 divided by its wavelength, which is 0.18 meters, and the frequency is 1833.3 hertz. But to determine the time-based setting in seconds per centimeter of the CRO, so now the time interval for this wave is going to be 1 divided by the frequency, 1833.3 hertz, and we get a time interval of 5.45 into 10 to the power of -4 seconds, which means that from here, from this point until this point, it's going to be total 5.45 into 10 to the power of -4 seconds. And this whole comprises of 26 small boxes, meaning counting from here and ending here, we're going to have 26 small boxes. Now 1 centimeter of this larger box has got 5 small boxes, counting from here 1, 2, 3, 4, 5. This 1 centimeter comprises of 5 small boxes, and this whole wave this whole one complete wavelength of wave comprises of 26 small boxes. Now 26 small boxes is 5.45 into 10 to the power of -4 seconds. Now for 5 boxes, it's going to be of 5 into 5.45 into 10 to the power of -4 divided by 26, which is 1.05 into 10 to the power of -4 seconds, which means that we're going to have a time-based setting of 1.05 into 10 to the power of -4 seconds per centimeter. Part 3, the intensity of the sound from the loudspeaker is now halved. The wavelength of the sound is unchanged. Assume that the amplitude of the trace is proportional to the amplitude of the sound wave. On figure 4.1, sketch the new trace shown on the screen of the CRO. Now, intensity is directly proportional to amplitude squared. Suppose that intensity of this waveform is 1, and amplitude of this waveform is this in total is 2, and this in total is 2, and then 2 units more, that would make up 2.4 centimeters. Now intensity will decrease by half. This means 1 by 2, and this is directly proportional to amplitude square, so the newer amplitude is going to be of root 1 by 2. So root 1 by 2 is 0.707. This means that every time you decrease intensity into half, your amplitude is going to decrease by 29.3%. So this time your amplitude would be decreased by 29.3 divided by 100 into 2.4 centimeters. This means that there will be a decrease of 0.703 centimeters from 2.4 centimeters, which is equals to 1.7 centimeters. This means that now your newer waveform will have an amplitude of 1.7 centimeters with the same frequency, and same time period. So 1.7 centimeters is going to be, this is 1, this is 1.246, and this will be 1.7 centimeters. So starting from here, we'll start from here, we'll have our maximum here, and then we'll end here. Again, we're going to have our minimum here, and then we'll end here. So this way we're going to have this new waveform. So this kind of waveform will now form when your intensity has decreased by 2 and your amplitude will decrease by 29.3%, since they are directly proportional to each other. Part C, the loudspeaker in B is held above a vertical tube of liquid as shown in figure 4.2. A tap at the bottom of the tube is open so that liquid drains out at a constant rate. The wavelength of the sound from the loudspeaker is 0.18 meters. The sound that is heard first becomes much louder when the liquid surface reaches level A. The next time that the sound becomes much louder is when the liquid surface reaches level B, as shown in figure 4.3. Part 1, calculate the vertical distance between level A and level B. So the first sound heard is when the waveform is going to be of like this, where the length of this tube is going to be lambda by 4. The next sound heard would be when the new waveform forms like this, when there's going to be an antinode on the open end, and at the closed end there's going to be a node where this length of the tube is going to be 3 by 4 of lambda. Now the third possible sound will be heard if the waveform has a pattern like this, where there's going to be again an antinode on the open end and a node on the closed end, where this length of the tube is going to be 5 by 4 of wavelength. This is when the water level, when the liquid level reaches level A, and this is when the liquid reaches level B. Now 3 by 4 of lambda, which is 3 by 4 into 0.18 meters, the length of the tube from the top level until level A is going to be 3 by 4 into lambda, which is 0.135 meters. And now from the top end until level B, this is going to be 5 by 4 into lambda, which is equals to 0.225 meters. So the distance from level A until level B is going to be 0.225 minus 0.135, and that is 0.09 meters. So from the top end until this level A, this is 0.135 meters. From the top end again until level B, this is going to be 0.225 meters. So the difference in these heights would be 0.225 minus 0.135, and that's 0.09 meters. On part 2, on figure 4.3, label with the letter N the positions of the nodes of the stationary wave that is formed in the air column when the liquid surface is at level B. So they're asking us to label all the nodes forming when the liquid level reaches point B. So the waveform at level B is going to be having how many nodes and antinodes? We're going to have 1, 2, and 3 antinodes, and we're going to have 1, 2, and 3 nodes. So the first node is at level B. So we're going to have N over here. The second node is going to be after half the wavelength, which is 0.09 meters from first node, and that's on level A. So again, N over here. The third node forms is when the length from first node is 0.18 meters. This node, this is going to be covering the whole wavelength from here until here. But since that can't be exactly labeled here, we're going to ignore that one. So we're going to have 2 ends labeled in figure 4.3. Part 3, the mass of liquid leaving the tube per unit time is 6.7 grams per second. The tube has an internal cross-sectional area of 13 centimeters square. The density of the liquid is 0.79 grams per centimeter cube. Calculate the time taken for the liquid to move from level A to level B. So first we should be calculating what grams of liquid is going to leave from A towards B, and that's density into volume, which is 0.79, and volume of the liquid is going to be area into the length. The area of the cross-sectional area of the tube is 13 centimeters square into length, which we must convert into centimeters. So 0.09 meters will be converted into centimeters, which is 9. And we get 92.43 grams of that liquid, which moves from A to B. Now 6.7 grams of liquid travels in each second, so 92.43 grams of liquid will be traveling in 92.43 divided by 6.7, and that's 13.8 seconds. Question number 5, part A, state Kirchhoff's second law, that is, sum of EMFs is equals to sum of PDs across the whole circuit. Part B, 2 batteries, each of EMF 6 volts and negligible internal resistance, are connected in series with 3 resistors. Resistor X has a resistance 4 ohms and resistor Y has resistance of 1.5 ohms. Part 1. The resistance R of the variable resistor is changed until the voltmeter in the circuit reads 0. Calculate the current in the circuit. So current is going to remain constant across 4 ohms, 1.5 ohms of resistor and resistor R. So voltage is equals to EMF is equals to resist into the current across it, which is I, and hence we have I is equals to 1.5 amperes. Now the resistance R, so when batteries with their positive and negative panels, they are facing each other, the total EMF of the circuit is going to be the sum of their individual EMFs, which is 6 plus 6, that is 12 volts. Now applying Kirchhoff's second law, which is sum of EMF, which is 12 volt, is going to be the sum of all the PDs across each of the components. So now PD across each component is going to be PD across resistor X, PD across resistor R, and the same across resistor Y. So PD across resistor X is going to be 4 into current across it plus resistor R into I plus 1.5 into current across it. As we now already have the current across each of these components, which is 1.5 amperes, we can calculate the value of resistor R, and that's 2.5 amperes. But two resistors X and Y are wires made from the same material. The diameter of the wire of X is twice the diameter of the wire of Y. Determine the ratio. So current is equals to N into A into V, which tells us that average drift speed is inversely proportional to cross-sectional area. So average drift speed of free electrons in wire X is going to be 1 divided by its area. Its area is twice the area of the wire of Y. So when we increase the area by 2, the average drift speed of free electrons in X will decrease by 4. So the average drift speed of free electrons in X is going to be 1 by 4, and the average drift speed of free electrons in Y is going to be just 1. So 1 by 4 divided by 1, we are going to have a ratio of 0.25. Part 3, the resistance R of the variable resistor is now increased. State and explain the effect of the increase in R on the power transformed by each of the batteries. So when resistance of the variable resistor increases, since they all are in series connection with each other, the total resistance of the whole circuit is now going to increase, which decreases the value of current across the whole loop since they are inversely proportional to each other, and as a result, power transformed by batteries is going to decrease. So we can write that total resistance of the circuit increases current decreases, and as a result, power by each of the batteries decreases too, as they are directly proportional to each other, power and current. Question number 6, part A sample of radioactive isotope emits a beam of beta minus radiation. State the change, if any, to the number of neutrons in a nucleus of the sample that emits a beta minus particle. So a neutron changes to a proton in beta minus decay. So we can write that the number of neutrons decreases by 1 in the nucleus of that sample. For B, the number of beta minus particles passing a fixed point in the beam in a time of 2 minutes is 9.8 into 10 to the power of 10. Calculate the current in picoamperes produced by the beam of beta minus particles. So current is equals to charge divided by time. The amount of charge is going to be the number of beta minus particles into the charge of each beta minus particle, which is 1.6 into 10 to the power of negative 19 divided by the time. So the number of beta minus particles is 9.8 into 10 to the power of 10 into the charge of each beta minus particle or an electron is 1.6 into 10 to the power of negative 19 divided by the time interval. That's 2 minutes. We'll convert that to seconds. So we'll have a current of 130 picoamperes. Part C suggests why the beta minus particles are emitted with a range of kinetic energies. So along with beta minus particles, we are going to have antineutrino also being released in beta minus radiation. So some energy will be shared with those antineutrinos. So we can write that other than beta minus particles. Antineutrino also released, with which energy is being shared. So that was the end of the paper. Thank you for watching.